Welcome back, everybody. This short lesson is going to deal with looking at Chapter 1, Measurements in the Scientific Method. Okay, so a lot of this chapter is hopefully going to be review and a little easier than naming because it's a topic that you studied every year in whatever science class you took. Okay, a lot of you took physics last year. It's something that you dealt with in that. How to measure, what is the scientific method, and how do you do science, okay? Before we get to that, I want to take some time and go over naming, give you some more practice. Again, I know it's a topic or a subject a lot of us could use all the practice we can get, so I'm taking a minute and I'm going to practice a few more naming and writing formulas. So take a minute, pause the video, kind of for today's warm-up for video number 2, is try to name or write the formulas of these compounds. Okay? So take a minute, pause. All right. So hopefully the first step you're doing always is identifying ionic or covalent. Okay, lithium is a metal, ionic. Copper is a metal, ionic. Sulfur is a nonmetal, fluorine is a nonmetal, covalent. Ammonium carbonate, ammonium is a polyatomic ion, therefore it's ionic. Dinitrogen pentoxide, covalent. Again, giveaway there is the prefixes. Okay? All right, so let's start with number 1. Lithium. Because it's ionic, I need to ask, is the metal a transition metal? In this case, no. Therefore, I do not need Roman numerals, so I just name the metal lithium. Sulfate is a polyatomic ion, so I don't need to do anything to its name. I just name it lithium sulfate. Number 2. Copper sulfide. Now in this case, the metal copper, okay, in this case, the metal copper is a transition metal. So I need to figure out its charge. To do that, I look at the anion first, or the negative half. Sulfur has a negative 2 charge, and there's only one of them, so this half has a negative 2 charge. Copper, then, to equalize that charge, remember everything's going to add up to be neutral, unless it's stated, it must have a plus 2 charge. That's going to make my name of this compound copper 2 sulfide. I need to include that 2 in the name because it's a transition metal. Number 3, I use my prefixes here. I don't use a prefix for the first element because there's only one. Remember, I don't use mono as a prefix for the first element, but you use it for the second element. The prefix of the first element will get, or the first element will get a prefix if there is more than one. But in this case, there's only one, so it's just sulfur. The prefix for 4 is tetra. Remember, the second element ends in IDE, sulfur tetrafluoride. All right, number 4, ammonium carbonate. So ammonium, I look up the charge. It's ionic, so I'm going to be crisscrossing here. Ammonium is +1, carbonate is -2. I find those charges on the back of my periodic table. I crisscross and end up with NH4,2CO3. Remembering, because I've added a subscript to a polyatomic ion, I put that polyatomic ion in parentheses. Number 5, it's covalent. So I can just look at my prefixes to write my formula. Dinitrogen pentoxide. Okay? All right. So, like I said in this video, hopefully quick on scientific method and measuring, we are on Chapter 1 notes, okay? So, scientific method. Okay, what is it? What are we doing? Well, the scientific method allows scientists to do science. You can't draw scientific conclusions without following at least pieces of this method. Okay, in order for other scientists to agree with you and for you to be able to draw conclusions that are valid, you need to follow this method. It's always going to begin with an observation. And again, every scientist uses specific methods specific to their inquiry, okay, or their investigation, but all scientists are going to have some things in common in order to draw scientific conclusions. And it's always going to start with making an observation, okay? Making an observation. In regular chemistry today, I talked about, I was in a canoe, a friend threw me a soda, and some sodas sank, and some sodas floated, okay? I observed something. That was a qualitative observation because I didn't make a measurement. If I made a measurement, okay, that would be a quantitative observation. Remember, quantity. Both are as important. Make sure you're making both throughout your experiments, okay? So I made an observation. Some sodas floated, some sodas sank. And then I formulated a hypothesis. Hey, maybe it's because it's diet or regular. Maybe diet floats and regular sinks, okay? There's an example of taking that observation, taking it one step further to formulate a hypothesis. After I form my hypothesis, I'm ready to perform an experiment to test it. Okay? I could buy a bunch of diet sodas, throw them in a container of water, see if they float. Do the same thing with regular sodas, throw them in a container of water, see if they float. Collect data on which ones float and which ones sink, and see if I can draw a conclusion as to what type of soda, regular or diet, floats and sinks. I may have to go back and maybe both of them float or both of them sink. Okay, I may have to go back and redesign an experiment and start looking at other variables to change to draw a conclusion as to which sodas float and which sodas sink. But in this process, I'm always following these three main steps. In order to do science, you make an observation. You formulate a hypothesis, you perform an experiment, and you draw conclusions. Okay? All right, so like I said, depending on what source you look at, depending on what teacher you listen to, there's all sorts of different maps for the scientific method and different steps for the scientific method. I'm going to say the three most important you need to understand are asking a question or doing an observation, constructing a hypothesis, and performing an experiment. Over time, that experiment can draw a conclusion, and if other scientists test it and other people validate it, eventually that conclusion can maybe become a theory or a law, which are backed up by a lot of data and a lot of agreement, okay? Theories and laws have proven the test of time in many ways, okay? They can be changed. Nothing in science is permanent, okay? We're always looking for new data to change things or support new information, okay? But both of these have been validated over and over again. A theory explains why, and a law describes things, okay? For example, the theory of evolution explains why we have this diversity of species, why giraffes have long necks, why turtles have hard shells. Laws, like the law of conservation of mass and matter, matter is neither created or destroyed. The law of gravity, okay? Two objects that have mass have an attractive force. These just describe what we have noticed, okay? They are descriptions. Theories explain why, laws describe, okay? A common misconception is that a theory can become a law. It is not that way. Theories, okay, explain why, laws summarize, okay? All right. They both are based on hypotheses. They both have a lot of evidence supporting them. They both can be revised, but again, a theory does not become a law. They're two separate things, all right? And when I'm doing this scientific method, when I'm doing science, remember, a lot of my observations are going to contain measurements. Measurements always have a number and a scale. If somebody asks you how far is the middle school from the high school, you can't tell me 2, okay? If you tell me 2, I'm going to say 2 what? 2 blocks, 2 miles, 2 light years, what? So every measurement, make sure that we do throughout the year, and you'll do a lot, make sure you have a unit, and you communicate that unit. In science class, we're going to use these particular units that are used throughout the world, okay? The United States, for one reason or another, has a unique measuring system. The rest of the planet, most anyway, use the metric system, okay? Scientists work together internationally, so they want to be able to communicate easily. It's not easy to go over to Canada and look at the speed limit. A lot of Americans, I would say, get confused, okay? Kilometers, where can I find that? Gasoline in liters, okay? Well, I don't know how many gallons or how many liters my car typically takes. So when you're traveling, you're going to see a lot of different units that other countries use. It's the same way in science, okay? Except you don't need to travel to get familiar with these units. Science is an international subject. So in order to work together, we've come up with, or scientists have come up with, an international system of units that everybody uses to make sure when you compare data from one country to another, you don't need to do all of these crazy conversions. Okay? It's based off of mostly the metric system. So you're going to see a lot of these prefixes. Okay? Now, working in the metric system, we'll practice using it. You can use the metric number line, or you could use dimensional analysis. The metric number line, which maybe you've learned, I would say, in middle school. King Henry died by drinking chocolate milk. Okay, that's how I learned it. Okay? So what I can do is if I go from centi to milli, I move the decimal one place to the right, and that allows me to convert. So the metric system going between units is really easy because we're simply moving the decimal place. Okay? So conversions among the metric system, all it takes is moving the decimal. 18 liters to milliliters. Using my metric number line, I move 3 places to the right. 18 liters equals 18,000 milliliters. Okay? You could also convert using dimensional analysis, going from liters to milliliters. Liters is going to go on bottom. Milliliters goes on top. I multiply there and get my answer. We're going to focus more on dimensional analysis method Thursday or Friday. Okay? All right, so going from milligrams to grams, maybe take a second and pause the video. Going from milligrams to grams, I'm moving to the left 3 places, would be 0.45 grams. Okay? You could also use dimensional analysis and divide by 1,000. 20 kilograms to milligrams, I'm moving 6 places to the right. That's where I got that 20 million milligrams. I could also multiply by 1,000,000. Okay? So you can do this in a variety of ways. There's all sorts of different metric conversion diagrams that you can use, going from meters to micrometers. We're moving, it looks like 7 places, right? Or 6 places. Okay? 6 places to the right. Therefore, 20 meters equals 20 million, correct? 20 million micrometers. All right? Now again, if I'm moving a little too quick through this, that's okay because we're going to practice this more so in class. All right? Now when we're making these measurements, our measurements can be precise, accurate, hopefully both. Okay? Precise deals with how much they agree with each other. For example, okay, this person doing archery, it's kind of all over the place. I would say they're not precise nor accurate because we're assuming their target is the bullseye. Okay? This is precise. Not accurate because they're not hitting the bullseye. This is accurate and precise because they're close together and hitting the bullseye. Now you can't be accurate without being precise because if you're getting your intended target over and over, that's both accurate and precise. But if you only get your intended target once, and then you're all over the place, you can't say you're both, okay? Because if your data is not precise, it can't be accurate, okay? So you can be precise without being accurate, but you can't be accurate without being precise. Because accuracy depends on, are you getting the intended target over and over again? All right. Now, where we're going to wrap things up today is just how we measure things. Now, whenever I use an instrument to measure things, I'm always going to measure as precise as possible or as many decimals as the instrument allows, and then add one for uncertainty. Okay? So, you're always going to have one uncertain measurement. We're going to do a few practices today, but again, tomorrow in class, we'll do more. Okay? So, let's look here. This pencil, okay? This pencil, we can all agree, falls somewhere between 25 and 26. Okay? So, I can say it's 25 point something. All right? Now, can you necessarily say it's 25.6 or 25.7? No, because my instrument doesn't allow me to be that specific. So I went as precise as the instrument allows, and then I added one additional uncertain digit. I said 25.7. Maybe you said 25.6. Okay, maybe you said 25.8. Okay, what's important here is that you're in the ballpark and that you have the proper number of decimals. What you will be graded on my exams and the AP exams is, are you in the ballpark and do you have the proper number of decimals? Okay, so what this is saying, because that last digit is uncertain, is I'm certain this measurement falls somewhere between 25.6 and 25.8, which we can all agree, hopefully, it does. Take a second, try to measure this. What would you say this is? I would say it's it's somewhere between 3 and 4. Okay, so 2.3 something. Okay, 2.32. I can't say it's 2.3345. Okay, again, I went as precise as the instrument allows. I know it's somewhere between 2.3 and 2.4, and then I guessed on one digit. Okay, 2.32. So I'm saying it falls somewhere between 2.31 and 2.33. Again, your decimals is controlled by your instrument. Take a second. What would you say this is? Okay. I would say it falls somewhere between, these are each 6.2, 6.4, 6.6, falls somewhere between 6.6 and 6.8. So I'm going to say 6.6, and then I'm going to add an uncertain digit. I said 6.62. Okay? So do you have the proper number of decimals? You may not have exactly had 6.62, but ask yourself, do you have the proper number of decimals? A couple more. Make sure you're paying attention to, okay, what order this is. 39, 40, okay? So this is going to be 39 point something. You were not counting up here, we're counting down. This would be maybe a burette, and I'll show you these as the year goes on. Okay, so take a second, try to measure both of these. Let's start with number 1. Number 1, I would say it falls somewhere between 39.2 and 39.3. So maybe 39.24. Okay, I added one uncertain digit. Number 2, it falls somewhere between, this is 15 and 16. So maybe 15.9. So notice the difference here. Here, these units are tenths. These units are 1, or the lines. So this one was allowed me to be more precise or have more decimals than here. All right. Now this is a lot like question number 13 on your homework, which is the one question I'm assigning. Okay? So here, try to measure this. Somewhere between 37 and 38. Take a second, try to answer. All right. I would say it's 37.3 and 37.4. It looks almost like it's exactly on 37.3. But again, I know it's somewhere between 37.3 and 37.4, so I can add that additional digit for uncertainty. So 37.30. Again, I'm communicating how precise my instrument is. It tells me exactly the tenths. Therefore, I can go to the thousands when I'm, or the hundredths, excuse me, when I'm communicating my measurement. And again, make sure you have a unit. All right, so today, pass your safety quiz. Worksheet 1.2, doing number 1 through 8, practice naming. And try one measuring problem. Number 13 on worksheet 1.2. I apologize if I went too fast. Again, I'll try to make these a little slower. Today I wanted to get through it somewhat quickly because it's a review. But again, if you have any questions, feel free to set up a Zoom meeting with me today and we can get that answered. Okay? Hopefully this is enough information to get you able to do worksheet 1.2, number 1 through 8, and number 13. I'll see you tomorrow.